It's my pleasure to have the opportunity to introduce our speaker tonight, Dr. Nathan Niemi, who is Associate Professor at University of Michigan and is currently the Camp Davis Field Director. He has a 1994 magna cum laude degree from Cornell, 96 and 2002 Master's and PhD in Geology from California Institute of Technology. Professional positions, he's worked early on when he was in his academic career for the USGS, teaching assistant at California Institute of Technology, postdoc at MIT, assistant research scientist, UC Santa Barbara, and 2004-2006 member of the professional staff at California Institute of Technology. And then 2006 he made it to the University of Michigan, where he was an assistant professor until 2013, and since 2013 he's been an associate professor in the Department of Earth and Environmental Sciences at the university. Long list of publications, professional presentations, students that he's been an advisor for, research grants and services carried out for the department and the university. His research interest, which basically he's going to talk about here tonight, is focused on tectonics and in particular the understanding of the processes that control the deformation of continental plate interiors at timescales ranging from years to tens of millions of years. And certainly the Caucasus is a very fine example of that. So without further ado, I'd like to ask you to join me in welcoming Dr. Nathan Niemi.
Thanks. So I'm going to talk to you a bit tonight about the Caucasus and the research that I do there. I've been working in this part of the world for about 11 years now. It was a very strange occurrence that led to me starting there. I just accepted my job in Michigan, and the phone on my office mate's desk rang. My office mate had done his PhD in Iran. And the person on the other end of the phone said, "I'm from Azerbaijan. I'd like to work with somebody in the US on the Caucasus." And my office mate said, "Well, there's this guy next to me who just got a new faculty position. He's probably looking for something interesting to do." And handed me the phone. And so 11 years later, here I am working in the Caucasus. Broadly, my interest is in broad plate boundaries. And so when we think about the very basic concept of plate tectonics, it's these rigid plates moving around the surface of the Earth that interact along their edges on very, very narrow zones. There's a few places in the Earth, however, or in the world that doesn't really happen. The Western United States, for example, is one. You guys have a huge active normal fault here in the Tetons, and you're far, far away from the Pacific Plate, which is in California. And that whole western half of North America extends and deforms, and that was the subject of part of my PhD thesis. Tibet is another example where India is colliding with Eurasia, and the deformation zone extends thousands of kilometers from the plate boundary. And the Caucasus is another such example. Arabia is colliding with Eurasia, and the Caucasus are 700 kilometers away from where those two continents meet one another, and yet they're the highest mountain range in the whole deformational zone, and they appear to be very active and very young. So one of our questions is, why does deformation distribute itself over such wide regions, instead of saying very focused along the plate boundaries? What does that tell us about how the Earth behaves? And so one of the things I'll try and convince you of, I think, is that the Caucasus themselves are the very, very earliest stages of a continental collision. The last remnants of oceanic crust have disappeared just in the last couple million years, and two continental blocks have just begun the process of colliding. And that's nowhere else in the world can we potentially capture that, as far as I know. And so it's a really interesting place to look at from that perspective. But I'll talk a little bit about what else is interesting about the Caucasus. I don't know how many have been to that part of the world. I'll talk a little bit about the tools I use to study the Caucasus, and kind of put together a story of why we think this is a really unique place where more research should be done. Thank a number of people. I have graduate students at Michigan who work with me on this project. I've collaborated with Eric Kogel, who's a professor at University of California, Davis, for 10 years on this project, and his graduate students. Adam Forte was an early graduate student there as well. We work with local institutions. There's a Geological Institute of Azerbaijan we work with closely, Ilia State University in Georgia, and I work with Andrei Kudulay at St. Petersburg State University for work in Russia. And so these are the three countries, Azerbaijan, Georgia, and Russia, that we need to work in the Greater Caucasus. And then I've worked with a number of other people to do some of the techniques that I'm going to explain today that we use to probe the evolution of the Caucasus. None of this would happen without funding. National Science Foundation has been a big source of our support. The Civilian Research and Development Fund, which was a spin-off from the State Department, is a source of our support. and University of Michigan's International Institute supported my graduate students in working overseas. So where are the Greater Caucasus? If you're not familiar with their location, they lie between the Black Sea and the Caspian Sea on the southern margin of Eurasia, right along the border between Russia, which is this part here, Azerbaijan over here, and Georgia. The plate boundary, accepted plate boundary between Arabia and Eurasia is all the way down here along what's called the Bitless Suture. So this deformation zone is 570 kilometers wide, and the Greater Caucasus is the northernmost element. With all due deference to France, this is in fact the highest mountain range in Europe. So the peak of Mount Elbrus here in the Greater Caucasus is approaching 6,000 meters elevation. It's a stratovolcano that sits on top of the range. I didn't have time. I should have put the Wyoming range here for scale. The last time I gave this talk, I was in California. But this is the Sierra Nevada mountain range for scale, with Los Angeles down here, the Bay Area up here, and the Greater Caucasus shown at the exact same scale. So it's roughly the length of California. The top topography is also scaled similarly, and so you can see it reaches higher peak elevations. The prominent stratovolcano here at the end of the range stands out quite significantly. This is just one of the reasons we had the opportunity to learn a bit about this part of the world. So again, this is Georgia, Azerbaijan, and Russia. And some of these places you guys may have heard of in the news: Ossetia, Abkhazia, Chechnya, Dagestan, places that make it not so easy to work in this part of the world. When I started working here in 2006, we were actually really fortunate that the 2014 Winter Olympic Games were going to be in Sochi. And so it turns out there was quite a bit of détente between all these countries for a period of about 6 years that made it much easier to get in and start establishing contacts and start doing field work. So just leading up to the Winter Olympics was the one time I had the opportunity to actually work on the Caucasus side, or sorry, the Russian side of the Greater Caucasus. Most of my work focuses here in Azerbaijan, with a little bit of work in Georgia, and we're going to start this coming summer, actually later on, working in Armenia as well. But we're really lucky to have this kind of opportunity to get our foot in the door and start working here. All right. So why study the Greater Caucasus? What are some of the interesting things about the range? From a human perspective, resources, it's incredibly resource rich. This is a natural oil seep. It's just a spring of oil coming out of the ground on the side of a hill in Azerbaijan. And these are fairly frequent in the part of Azerbaijan adjacent to the Caspian Sea. There's also huge mud volcano fields, which are really spectacular. They're carbonated by natural gas, and they just bubble and explode natural gas carbonated mud and build these huge shield volcanoes that erupt. So this is actually the caldera of one of these mud volcanoes bubbling away with liquefied mud carbonated by the gas, and when they're dried up, they leave behind these little spatter cones of mud that they bring up. So it's very resource intensive, and exploration, particularly offshore, continues to be ongoing in the Caspian Sea in Azerbaijan. It's also a region of very high seismic risk. And so here's some, these here in particular are what are called isoseismals. They're guesses of the degree of shaking from an earthquake that happened back in 1191. And we actually have historical records of earthquakes going back that far in this part of the world. Historically, I'll work way backwards. The biggest historic earthquake is a 6.9 here in Racha in Georgia. Happened in 1991. Killed about 300 people. Some of you, I'm sure, remember probably the Spitak earthquake in Armenia in 1988. That killed 25,000 people here in Armenia. In Ashgabat, which is just on the other side of the Caspian, there at that exit sign, in Turkmenistan, there was an earthquake in 1948 that killed 110,000 people. And here in this area, there are repeated earthquakes, 1139, 1191, 1859, 1872, 1902, that are thought to be in the range of 7.5 to 8 magnitude earthquakes. There's a historical record of 115,000 people killed here in the 1139 earthquake. So these earthquakes are huge, and the population centers here have only grown since. Baku is a major international oil city. Tbilisi is quite large. An event like this that happens today would be devastating for these countries, both for the infrastructure in the major cities, as well as the massive resource infrastructure that extends from the Caspian Sea right through this major deformational belt out to the Black Sea in order to get natural resources to Europe. All right, so we want to understand to some extent what's the tectonic setting of this area, and what kind of earthquakes can we expect to have. This is just another example of what happens in this part of the world. This is actually, again, historically recorded during the 1139 earthquake. This entire side of a mountain collapsed. You can see two lobes of landslides coming down, one here and one coming down here. Both of these lakes only exist because the landslides came down and dammed these valleys. And so there were villages in here that were buried as a result of these types of landslides. And this kind of topography exists all throughout the Caucasus. This happens when large seismic events happen. I had 20 students today. Have any of you guys ever been to Blowout Canyon? No? So if you go down to Alpine and you turn right at Alpine and drive up along Palisades Reservoir, not quite to Big Elk Creek, there's a camp sign. The sign says Blowout Canyon Campground on the left-hand side. On the right-hand side, there's a little Forest Service road that wanders back up in there, and there is one of these that's probably 1,000 years old. And it actually, the top of the mountain collapsed, and it ran all the way down Blowout Canyon, and it actually went out into what is today the Palisades Reservoir. Old air photos from before they filled the dam show that it made it all the way out to the Snake River. So it's about 6.5 kilometers long. And one of the things we're doing with our students is using laser scanners as part of our teaching exercises to ask how much mass moved during this slide. So if you guys ever need an interesting field trip, it's like walking on the moon. You drive through this beautiful Wyoming forest, and you come up this landslide with blocks the size of houses that have no trees, no vegetation. A spectacular place to go and look. And this is a similar thing, just roughly, probably even roughly the same age.
The mountain, is that all sedimentary rocks or volcanics?
Here,
Yes.
this is actually in the Lesser Caucasus, so this is mostly volcanoclastic sediment. So it's volcanoclastic sediments. The Lesser Caucasus was an arc in Cretaceous time, and then shed off the arc were lots and lots of sediments that are made of andesitic debris. This is just an example of the active tectonics of this part of the world. So what you're looking here are what are called wind gaps. And so below the Earth's surface here is a thrust fault that's coming up towards the surface, and it's deforming the surface of the Earth and folding it. And rivers coming out of the Greater Caucasus are trying to defeat this fold and failing. And so progressively, these different river channels are abandoned as the fold gets too big and grows too fast for the rivers to cut through. And so these are now wind gaps with no water in them. This is a digital elevation model showing topography. And so the river now comes and goes all the way around this active fold and spills out here between these two gaps at the end. And so as a function of time, as this has grown and propagated this way, the river's been getting defeated. And this way we can look at the interactions between tectonic structural growth and climatic processes and fluvial processes. And this is active, ongoing. I'm sure there's earthquakes under this. We don't know of any in historic time, but earthquakes will happen and raise this fold more in the future. And Baku sits just off over here. And lastly, it's not recognized as widely, but there's volcanism throughout the Greater Caucasus. Elbrus here, as I said, is a stratovolcano that sits at almost 6,000 meters. It last erupted between 0 and 100 AD. Kazbek is another volcano that is potentially active. It has hot fumaroles surrounding it. One of the big concerns for the Georgians is a volcanic eruption that would actually trigger landslides off of the volcanic mass. The main highway between Georgia and Russia goes right by Kazbek. And the funny thing is they're not worried about the highway being closed. What they're worried about is the Russians coming in to assist. Was the way they phrased it, I believe. Sorry, get used to these in a minute. This volcanism was only recent. This is a large volcanic field that was only reported in 2013. So there's a lot we don't know about this part of the world. And this one here, Chegem, it's kind of like a mini Yellowstone. It erupted 300 to 500 cubic kilometers of material about 2 million years ago. And there are granites associated with it that are 2 million years old that are now at the surface of the Earth. So it's a very, very active volcanic area as well as tectonic area. And so these are things we're interested in, and our colleagues in particular, this is their interest. How can we help them build infrastructure to understand these threats? That's their biggest, whether or not this is the initiation of a subduction zone is to them much less interesting than when that volcano erupt, what might the impacts be of a large earthquake in this part of the world. But we can give them framework to try to understand those problems and those concerns. So a little bit of tectonic framework. So the Caucasus are part of the large alpine Himalayan collisional belt that extends all the way from Europe through Asia. And so at various points we have India colliding with Asia to form the Tibetan Plateau. This is one of the classic continental collisions in the world. A large ocean belt was consumed and two continents collided, Asia that forms the Tibetan Plateau on the north and India colliding from the south. The Caucasus sit off to the east of here and have a somewhat different tectonic setting. We have the Arabian platform down here, which is a large continental mass. Up here, this is what we call Scythia, is basically the southern margin of Russia and Eurasia. But in between, we have kind of a tectonic train wreck. You can imagine, for example, the Indonesia having a continental collision. All these little islands and fragments and pieces are getting amalgamated and assembled and colliding together with one another instead of just having a simple two continents trundling along until they collide. All these pieces are getting smashed up along the way. So it's a much more complicated collision belt. That makes its evolution quite a bit more complex. The Caucasus lie right on the very southern margin of Scythia. Below them, as I mentioned, lie the Lesser Caucasus Arc. One could imagine, for example, probably the simplest analogy would be Japan eventually slamming back into mainland China with the oceanic basin behind it closing as other continents came in from the south. So it's a big Cretaceous volcanic arc that's now currently colliding with the Greater Caucasus, a large mass of oceanic material getting piled up here in the Anatolian Plateau, and finally the ancient Arabian continent colliding and pushing all this northwards into Asia. At least two oceanic belts have closed along this region, Paleotethys, which closed in the Jurassic, and Neotethys, which has closed in the last roughly 30 million years. This is the same ocean basin that closed to allow India to collide into Eurasia as well. A comparison of the size and relief of these two collisions. I've had the fortune to work in Tibet for a few years as well. Greater Caucasus are somewhat more tractable, and we have an opportunity here to see all the way across the mountain belt. In particular in Azerbaijan, we can work our whole way around it. It's quite a bit more accessible, lower elevation, and quite a bit more opportunity to work and see much of the geology across the entire collision zone as opposed to something this massive, although they're part of the same overall alpine Himalayan collisional system. The other interesting thing is from corner to corner here in the India and Eurasia collision, we have Precambrian Indian shield across the entire extent. So we have two continents colliding with one another. The Caucasus are quite a bit more complex than that, as I've mentioned. And so we have oceanic crust under the Black Sea, Precambrian crust, much like India here in the central portion of the Caucasus, transitional crust that was probably thinned during rifting in Jurassic time here in Azerbaijan, and then more oceanic crust out here in the Caspian. So we have an opportunity to look at many different types of crustal collisions and how they behave as all of these pieces get collided northwards into Eurasia. Very different rheologies, very different strengths, very different densities. Oceanic crust is very strong, very dense, will likely want to subduct beneath Eurasia. Here, the Precambrian Massif, we have these two pieces of continental crust that both want to collide. Neither one's going to want to give way. Transitional crust here may subduct underneath Caucasus, and then again here we have oceanic crust again very well, may likely subduct. This is what we're going to focus on, one, because one of the issues about the Caspian, of course, is any boat in the Caspian is built there, right? You don't bring them in from somewhere else, so it's not very easy to get a vessel into the water. And the other is a lot of Iranian coastal waters down here are difficult to access. So we primarily focus here on this transition here from transitional crust in the east to Precambrian Massif in the west, and what that means for behavior and the evolution of the Greater Caucasus. And so one of the reasons we're interested in this, it is a kind of a complicated diagram, but what I'll try and explain briefly is we could do these global plate reconstructions where people look at magnetic anomalies on the ocean floor and ask how far, for example, has India traveled with respect to Asia as a function of time. And the answer is typically on the order of thousands of kilometers. India was much further south and has moved north before eventually colliding with Asia. If you look at Asia, though, and ask how much has Tibet shortened, the answer is much, much, much less. All right? And so one of the questions we're curious about this initiation of continental collision and subduction and this orogenic process is how do you account for that discrepancy? One answer is you shove a lot of India underneath Tibet. That's one of the current thinkings, is that India itself may extend this far north beneath the Tibetan Plateau. And so instead of crumpling everything up, you shove one thing under the other. And these discrepancies exist in many mountain belts around the world, and the Caucasus is one. This is just a summation here of how much shortening we see in Asia in the green, how much we see in the colliding continent, whether it's India or whether it's Arabia, And then the total length of the bar is how far this piece of continent has moved northward with respect to Asia as a function of time. And so we can see we're missing, in many cases, 50 to 60% of the total shortening from plate reconstructions when we try and look at the structural geology and ask where is that accommodated. So this is an interesting question we're trying to resolve as we look at the evolution of these mountain belts as well. Okay, so I'll give you now a few modern observations for the tectonics of the Greater Caucasus and some of the tools that I use to look at the evolution of this mountain belt. It's just a general geography to get you guys oriented. So this is, again, Black Sea and Caspian Sea. You'll see them in many of the images. The Absheron Peninsula, where the big city of Baku in Azerbaijan is. The Greater Caucasus are the ranges to the north here, and they're largely cored by late Paleozoic granitic rocks covered by Jurassic sedimentary rocks. Colliding with them from the south is the Lesser Caucasus, which is an island arc that formed in the middle of an ocean. See, these are all granitic rocks that are largely Jurassic to Cretaceous in age. Intervening is this large sedimentary basin that is filling as these two mountain belts collide and shed sediment from both the north and the south into this large basin. This is a work from Rob Riley during 2007. And what you're looking at here are GPS velocities with respect to Eurasia from all throughout this greater Middle Eastern region. Rob is incredible at making international contacts and getting data from very difficult places like Iran. I think he was one of the first US scientists to work in Turkmenistan. And he built GPS receivers stations throughout the Greater Caucasus region. And so we're going to zoom in and look at some of the data here in the Greater Caucasus. And so the coloring scheme I'm using here is red are GPS velocities in the Lesser Caucasus, orange are in this intervening basin, and then yellow are those that are attached to the Greater Caucasus. And so I think most of you are probably familiar with something like this, but if you're not, these are just very similar to the GPS you have on your iPhone to use with Google Maps or something similar, except quite a bit larger. The antennas are about this big around. And they give us, if we let them sit out there for several days collecting data in one spot, we can get relative motions to a precision of a couple millimeters. Here in the Western United States, some of you guys may be familiar with the EarthScope project, where these are actually drilled into solid rock and sit out there for years, and we can get relative motions with precisions of fractions of millimeters. And so these here are set up for just a few days at a time, and the equipment's moved from site to site to make these maps. And so obviously the length of the arrow is how fast it's moving, and then the orientation is which direction it's moving. And so this is just an expanded version on the Greater Caucasus region. And so here is the Lesser Caucasus. Here, the Kura Basin, that intervening sedimentary basin, and over here, the Greater Caucasus. And I'll show you some data from along two profiles. One Western profile, what we're going to be looking at is the rate of GPS motion in the direction of the plate collision. And so how fast are the stations moving in this direction? Then we'll do the same thing over here. We'll look at how fast are the stations moving in this direction.
Is the white arrows in the Arabian continent?
The white arrows are actually ones I didn't particularly focus on in this study, but here's the bitless suture. So this group down here is in Arabia, and this group in this area here is what's called the East Anatolian accretionary complex. So Arabia down here, here's the East Anatolian fault coming over to Turkey, the North Anatolian fault. So yeah, Arabia down here, Eastern Turkey, Eastern Anatolia accretionary complex. This is mostly in Armenia. And then Lesser Caucasus, Kura, and Greater Caucasus. All right, so in the west, what we see is that there is some, but a very minor amount of motion of the Lesser Caucasus northward towards Georgia. And so this is the western transect. So you can see that the average velocity of the Lesser Caucasus with respect to the center of Asia is about 5 millimeters a year or so. The average velocity of the Greater Caucasus with respect to Eurasia is within a millimeter. So basically they're not moving with respect to Eurasia. They're on the margin of it. And there's a step function on the north side of the Greater Caucasus where this velocity changes. And so we see about 4 millimeters a year, maybe a relative motion of Lesser Caucasus northward colliding with Asia. As we move just a little bit to the east, you can see that the scale changes. The scale is the change, but the position of the points changes dramatically. The Lesser Caucasus over here are moving as much as 12 millimeters a year northwards, right, into Asia. The Greater Caucasus, of course, are still more or less stable with respect to Asia. And so we've more than tripled the velocity of the Lesser Caucasus with respect to the Greater Caucasus. And you can think about that and ask, how might you do that? And there's two basic ways. One way would be that you have a big fault in the middle that lets this block slip northward much faster than this block. The other way is you're swinging the whole thing shut like a trap door and pivoting it around a hinge, right? So that on the east side you're moving much faster than you are on the west side. And so this observation was made, as I said, in 2007 by Rob Arlinger, and shows that the conversion rates are changing dramatically over a very, very short distance. If you went to California and looked at GPS velocities, you would not see these kinds of dramatic changes. And so we began to be curious about what this might mean for the evolution of the Greater Caucasus. The seismicity is actually fairly consistent with what you'd expect. If you have two plates that are grinding together much faster, you're probably going to need a lot more earthquakes. Shouldn't shock anybody, I think. And if we look along the range from west to east, we see a very, very similar pattern in terms of the seismicity. So this is the sum, just cumulative sum of how much energy is released by earthquakes in the historical catalog, roughly the 1950s in this part of the world. And each little purple bar you see here is an actual earthquake. All right, and so in the western part of the Caucasus, over here, where they're colliding much more slowly, you see far fewer earthquakes, right? Much less total strain accumulator, seismic release occurring. Over here in the eastern part, when we start to pick up steam and those two plates are colliding together much more quickly, you see there's far more earthquakes here in the eastern Greater Caucasus. And obviously the total seismic moment release is much greater. So those two pieces of data fit together in a fairly simple conception. Colliding slowly, fewer earthquakes; colliding faster, greater earthquakes. This is just a plot of elevation as a function of distance along the Greater Caucasus. And this was a little more surprising to us. Here in the west, the average elevations, even though it's colliding more slowly, are a little bit higher than here in the east. But overall, there's not tremendous variation in the amount of elevation variation. So this we weren't quite sure what to make of. It didn't necessarily support, it wasn't clearly obvious that this is what would result in that, but it wasn't clearly obvious that this was discrepant with these previous observations of deformation. And then the last thing we did was we started looking at the long-term history of geologic deformation in the Caucasus. And this is where we got a bit of a surprise, and then I'll talk about some of the data we used to try and understand this. So here in the western Greater Caucasus in Georgia, what we saw was that exposed at the surface of the earth, at the core of the Greater Caucasus, are these Paleozoic igneous rocks related to a much earlier phase of deformation. And stripped off of this mountain range here is a gigantic pile of sedimentary rocks of late Paleozoic through basically Cenozoic age. And if you go to the Russian geologic maps and ask how much strata was stripped off the top of the range, the answer was something like 5 or 6 kilometers of material has been removed. And this was interesting to us because in the eastern Greater Caucasus, over here, all that stratigraphy is still preserved sitting on top of the range. And this to us was a bit contradictory. We expected where you had very slow collision, slow deformation, fewer earthquakes, that you would not have uplifted and stripped and exposed so much of the range. And over here, where you had very rapid collision, very high rate of seismicity, that you would have had the opportunity to build higher mountains and strip off greater amounts of material. And so one of the first things that we did was begin to study the evolution of this. So we thought, okay, maybe this is slow, but it's been happening for much, much longer. That's one possibility. And this is going very rapidly, but it just started more recently. That was one way we could explain this. Another way we could explain it was potentially, this started much later. This was going faster earlier and has slowed down more recently. Right? We've had a change in how fast things are happening. And we started to apply some tools called Thermochronology to look at the rates of exhumation of the rocks in the Greater Caucasus. And so I'll show you some of that data and explain a little bit what it is. So have you guys had somebody talk about Thermochronology here before? Is that a term people know at all? Okay.
Only you at lunchtime.
Only me at lunchtime?
A couple years ago.
Okay. So thermochronology is a subset of geochronology, which is geo is just Earth and chronology obviously is time, right? And it's putting very very early on all geologic information in terms of time was relative, right? It was based on the fossil record, but there were no numerical numbers assigned to when any particular fossil existed. We could just see that there's a sequence that existed through time, and people could say, well, these rocks here are roughly the same age as these because they have the same assemblages of fossils. Geochronology and thermochronology are a method or mechanism by which we can put numerical ages on geologic events. And we use, they all pretty much work on the basis of radioactive decay. Right? And so we have radioactive parent elements decay to some daughter product, and by analyzing rocks and looking at the amount of parent and daughter product in the rocks, we can make an estimate for how old that rock is. In the simplest case, that's geochronology. Thermochronology is a little bit different in the sense that the clock, the radioactive clock, is temperature sensitive. And so for the example I will use in here in particular, we look at a mineral grain called apatite, which is a type of phosphate. And apatite incorporates uranium and thorium into its structure when it forms. Those uranium and thorium undergo decay to lead, but part of that decay process is they make helium. And at temperatures above about 60 degrees centigrade, that helium can just escape right out of those crystals. Just like any of you guys ever fill up a helium balloon, it eventually dissipates. And so that little radioactive clock where the uraniums are ticking away and radioactively dispensing helium, the clock doesn't start ticking until the rock cools below 60 degrees centigrade. And that's only about 2 kilometers deep in the Earth's surface. So if the rock's buried any more deeply than that, the clock doesn't work. Right? You cool it off, the clock starts to work. And there's many, many of these that we apply in science and geosciences with many different temperatures. And it depends on either what the decay system is and what the mineral is. So for example, the mineral zircon, which is a far more robust mineral than apatite, the exact same decay scheme, uranium and thorium decay to helium, the clock for it starts at the temperature of 150 degrees centigrade. And so if you imagine we take a rock and we pull out all these little mineral grains, it's a lot of fun, you should do it sometime, and do these geochronologic measurements, what we get is when that rock was at a particular temperature, what time that rock was at a particular temperature. And so if we do many of these analyses, we can actually make a path of where the rock is as a function of temperature and as a function of time. Right? And so by doing that, we can look at the rate at which the rocks move up towards the surface of the Earth. And so that's something we do at the University of Michigan. And putting numerical constraints on the evolution of mountain belts lets us start asking far more pertinent questions sometimes than we can by looking at the broader scale stratigraphic or paleontologic constraints. So this is just, when I started working in the Greater Caucasus 11 years ago, I went through the literature to ask the question, well, when did the Greater Caucasus form? And the answers were 40 million years ago, 30 million years ago, 20 million years ago, 10 million years ago, 5 million years ago, right? And so by applying these numerical techniques, we can start to constrain what really is happening in terms of the evolution of the Greater Caucasus. And all of these are indirect measures of what's going on, looking at basin stratigraphy and assuming that relates to a process, as opposed to directly measuring when the Caucasus cooled or came towards the surface. So the basic application of thermochronology is in an active mountain belt. You have thrust faults that move rocks towards the surface of the Earth, building the mountains. But on Earth we have a climatic system, and so that climatic system attacks the mountain belts with rain and snow and glaciers, and erodes material and takes them off the mountains and carries them away. By eroding that material, you actually take particles of rock in the Earth and then bring them closer to the surface. Right? And so if there was no erosion and these two blocks just slid past one another, these points would just stay at a constant depth below whatever surface was moving up. But because erosion is tearing it down, these rocks, these samples, in effect, move towards the surface of the Earth. And at various depths then, because the temperature of the Earth gets hotter as we go down, at roughly 30 degrees centigrade per kilometer, right, we can track the rate at which these particles move towards the surface as these various clocks start kicking on. Right? And so that's the general concept here for thermochronology, is applied to understanding the evolution of mountain belts. And so this is just 2 different examples. I'll give you, this is from a place called Gold Butte in Nevada. And here, this is, I think, in graphical form, what I tried to explain in words. Each of these, you see 2 designations. One is the type of mineral that was taken from the rock for analysis, and the other following letters are the thermochronologic system that was used, the type of analysis that was performed. And so the hottest one, zircons here, with the uranium lead system, that clock starts at 900 degrees C. Basically, when a rock forms, this clock starts, and it's really robust. And as you look at these other systems, you can say they have different temperature sensitivities. Some all the way down to, as I mentioned, apatite helium, as low as 60 degrees C. And so for two rocks at different ends of Gold Butte, which is in southern Nevada. Different analyses were done that have different temperature sensitivities. And what was actually shown was this particular thing is showing a piece of crust cooling down from about 1.5 billion years ago. And this particular east end of the block was cool for a long time. It was near the surface of the Earth beginning around 1 billion years ago, and it stayed near the surface of the Earth since then. The other end of the block, this is a large detachment fault, a basin range type fault, exhumed this block about 20 million years ago. And so the deepest end of the block that got exhumed at 20 million years ago pops from 400 degrees C to roughly surficial temperatures right around 20 million years ago. And so these are showing you what temperature the two ends of the block were as a function of time by using these different techniques. And so we will use this type of approach in the Greater Caucasus. The other type of approach you can take, this is why I have graduate students, I'm not this crazy. But this is actually, this original example here is from a guy named Paul Fitzgerald who climbed up Denali. And he collected samples at different elevations all the way up Denali. And the idea is the sample at the top of Denali, in this case, this is all one method. Right? When did this rock cool below 60? When did this one cool below 60? When did this one cool below 60? When did this one cool below 60? Etc. And the idea being, as these rocks are moving towards the surface of the Earth, the rocks at the top of the mountain, of course, cooled first, and the rocks at the bottom cooled later. And so by going down the mountain and collecting these rocks, you can actually look, you can substitute space for time and look at the evolution of the mountain belt. And his understanding of this was it cooled slowly until about 5 million years ago, and then it began to cool much more quickly. All right? And so we can apply both of these approaches to understanding the cooling of the Caucasus. And so this is my student Boris Avdiv on the Bezengi Wall. It's one of the really famous climbing routes in Georgia. It's a 1.5 kilometer vertical cliff. So he and some colleagues from Russia rappelled down the cliff, collecting rock samples along the way to do this type of analysis. I stayed home, covered my eyes, and pretended I didn't know that was happening. And so I'll just show you some of the data we have from the Caucasus using these kinds of approaches. And so first I'll talk a little bit about the excavation of the Central Caucasus. As I mentioned, the Central Caucasus exposed these crystalline basement rocks. They've had all this stratigraphy stripped off the top. And looking at just the maps that the Russians have made, it suggests that 5 to 8 kilometers of material has been stripped off the top of the Greater Caucasus at some point in time. This is just a picture of the Greater Caucasus from Georgia, some beautiful trekking routes up through this part of the world. And this is kind of the border here between Georgia and Russia. And so what Boris did, this is his transect right here, scaling Mount Ushba and the Bezengi Wall, and some other samples here. We happen to have an opportunity to collect up near Mount Elbrus, which is located over here. And we collected these samples and looked at their cooling history as a function of time. This is kind of a cross-section across the range here. And so this is what's called the main Caucasus thrust. By many it's interpreted as the boundary between Eurasia, whatever lies to the south that's colliding with it. And this is the exposed Precambrian crystalline rocks, and then all the stratigraphy that used to presumably lie over top of this range has now been.
You just answered a question I was going to ask later, but I thought that was the main central thrust as it exists in the Himalayas, but it isn't.
No, it's not. And not many people work in the Caucasus, so when I give talks at professional conferences on the Caucasus, often I'm stuffed into sessions on the Himalayas, because we're just next door. Yeah. And so I sat there at a conference one day listening to Tibet or Himalayan talk after Himalayan talk after Himalayan talk, and I had main central thrust so crammed in my head I couldn't get it out when I talked about the Caucasus. So I kept calling it the main central thrust. You know, the main Caucasus thrust here in this part of the world. And so we'll look first at this group of data here on the Russian side of the border. And so in the core of the range, using what you're looking at here is a way in which we just run numerical models to look for cooling paths. So here we have temperature and time that match the data we've collected, whether it's up a vertical transect or we have one rock with many, many different types of analyses done on it. And so the core of the range, what you see here is that the models that we can use, the cooling histories that match the data we collected, require the rocks were very hot, relatively hot, at least 200 degrees C at 5 million years ago, and have come to the surface incredibly rapidly over that period of time. Again, at 30 degrees C, this is roughly coming from 6 kilometers depth all the way up to the surface in the last 5 million years. This is consistent with the amount of stratigraphy that appears to have been removed based on the geological mapping. On the margin of the range, I'll just flip back a second here. And so those samples are from right here in the deepest part of the core. On the margin, so here a sample that lies right underneath the stratigraphic cover. So one sample from here, another from over here. We see a different history. We see the rock started at about 100 degrees C or so, and then cooled slowly beginning around 30 million years ago. And so if there was a rapid exhumation of this sample beginning at 5, it was already so cool by 5 million years ago that our clocks wouldn't have been able to pick that up. And so one potential model for this, of course, is an evolving fold in which the core of the fold is coming up really rapidly and the margins are coming up more slowly. We also looked at the crystallization ages of these rocks using a variety of methods, and they give us ages around 300 million years ago. That's probably when these granites were in place during what's called the Variscan orogeny. And the rocks appear to have been in place originally at around 200 degrees C or so. And so they sat at roughly the same temperature, or perhaps got slightly buried, until they were re-exhumed in the last few million years, the deepest, most deeply exposed samples in the core of the range. So almost all of the cooling and exhumation is Cenozoic, and most of it is in fact Pliocene, very recent. This transect here is the transect down this very steep front of the Georgian portion of the Greater Caucasus, and it shows very similar results. This is a different method. Now we're using only a single sample collected at different elevations, but a similar result. Slow exhumation until roughly 4 or 5 million years ago, and then everything just rockets up to the surface at that point in time. So very, very young exhumation in the Georgian part of the Greater Caucasus, consistent with what we saw on the Russian side, not very far away. If we go, this group of samples all lies around here. If we go a little further to the west, a place called Say Valley, we can do a similar test. In this case, at a single Triassic pluton, and again, quite impressive. My students scaled this entire valley while collecting samples along the way. This is a part of Russia that I could not get permission to go to, but I did a beautiful job going up several hundred meters collecting samples. And get a very similar story, starting around 200 to 150 degrees Celsius, cooling slowly to about 5 million years, and then exhuming really rapidly after that time. So we're seeing this repeated pattern of kind of Pliocene rapid exhumation or denudation of the mountain range.
You said this was west of the first one? If you go back to your...
If I said that, I misspoke. Sorry.
Yeah.
East. Yes.
Okay, good.
Now John's got in my head with which is forward, which is backwards. Okay. Yes, it was, sorry, further to the east.
Right.
And so, yeah, this particular thermochronometer, zircon, which is sensitive to temperatures of 100, native 200 degrees C, tells us the rock was at least that hot 20 to 30 million years ago. And the rocks that we're collecting from crystallized only at 250 degrees C. And so these rocks have been buried for quite a while, and then were very rapidly exhumed, 5 or 8 kilometers in the Cenozoic. We think there's fairly slow exhumation, began at about 30 million years ago, and then much more rapid exhumation, almost 5 times faster, began roughly 5 million years ago in the Georgian portion of the Greater Caucasus. This is just kind of a summary of all the data. This is cooling rates as a function of time, but you can see it's very, very low in all. I didn't show you all of the transects we've done, but very low in all the transects, fractions of a millimeter a year, up until roughly 5 to 7 million years ago, and then suddenly it gets very, very rapid. So it's all the sediment begins getting stripped off the range just in the last few million years.
You're going to explain why that is the case?
No.
No.
Yes, I will explain in a minute why I think that's the case. I'll contrast it in a minute, but I want to look at the eastern Greater Caucasus, and then I'll come back and try to put this data all together in a coherent model. And so we've had a chance to work here, as I mentioned. Here we have a large gap. We would really like to know a lot. This is Chechnya here, this is Dagestan, and areas that just at this current time it's politically untenable to work in. But we are able to work here in Azerbaijan. You can actually see here's the border, the blue line coming through here. And Azerbaijan's really interesting because we can cross the entire range. We've collected samples across the entire width of the range there. Again, we have a fault that is the equivalent of the main Caucasus thrust. It separates the Kura Basin here from the main part of the range itself. So here we have Eurasian thrust itself, and here we have fractions or portions of the Lesser Caucasus that are colliding with it. And we have samples from both the Lesser Caucasus side and from the Greater Caucasus side. Or I should say the Eurasian side and the non-Eurasian side. Another way to look at it. All right. So samples north of the main Caucasus thrust, again, this is the Eurasian margin. This is equivalent to all the samples I showed you from Georgia. Right? So we have a really similar pattern in general in terms of deformation. They start off fairly warm, 100 degrees or so. Again, it's not surprising that these are not as hot because we're in the sedimentary cover. We're not down in the basement. We don't have any basement exposed in eastern Georgia, or sorry, in eastern Azerbaijan. So we're working here with Jurassic sandstones as opposed to the underlying Proterozoic basement. So they wouldn't have been buried as deeply. But they started at 100 degrees C, they cool slowly up until about 5 million years ago, and then they rapidly exhume to the surface. We see that with a couple samples that we've collected. Those are N1 and N2, which are just samples located here in the core of the Greater Caucasus. You can kind of see a big anticline in Jurassic sediments, and we're collecting along the axis of this anticline, the most deeply exhumed rocks we can find in this part of the range. When we step across the equivalent to the main Caucasus thrust, however, we see a really different story. These are volcanic rocks that we presume are related to the Lesser Caucasus arc. They're juxtaposed against the Eurasian margin, and in fact, one of the interesting things, get back here in a minute, is that these rocks here, you can see these are Cretaceous rocks in here. They are identical in age to the Cretaceous rocks here. All of these are very, very deep water, dolomitic shales, few fossils in them, probably deposited off a deep continental margin. These are volcanoclastic rocks with clasts in them this big around, being shut off of an andesitic volcano. And you can cross this fault here, and these two rocks of identical age are completely different character. So we know there's been some kind of significant juxtaposition right along this fault line. And so these rocks didn't exist until 100 million years ago. That's when the andesitic volcanoes began erupting them. And they actually exhume early, and then they get quickly reburied. Beginning about 30 million years ago, they begin to get reburied until about 5, and then they come back rapidly to the surface again. So unlike all the other rocks we saw, which started hot, cooled, and then rapidly cooled, these actually get buried for a while and never get particularly hot before coming back up again. And so I'll talk a little about why we think this is happening. There we go. Okay. So summarizing the thermochronology, on the southern margin of Eurasia, north of the main Caucasus thrust in what's clearly Eurasia, we seem to see 2 periods of exhumation. Slow exhumation beginning around 30 million years ago and continuing to about 5, and then rapid exhumation from 5 to the present. So we don't see any diachronating. It's not that the Georgian Caucasus are exposed more because they've been exhuming longer, right? Everything starts at roughly the same time. The slow phase of exhumation beginning at 30 coincides with most estimates for when the whole Arabia-Eurasia collision system began to happen. But the onset of this later rapid exhumation is not temporally correlated with any events along the Arabia-Eurasian suture zone, nor does it correspond, as far as we can tell, to any changes in relative plate velocities at this time. So something triggers the Greater Caucasus to start coming up 5 million years ago, but that seems to be 25 million years after this plate collision in the broader scale has already initiated. And so I'll kind of put these pieces together, I hope, into a story about the very early stages of continental collision and why I think that's what we're seeing in the Caucasus. So I'll recap what we said. In the Central Caucasus, really slow GPS rates, low seismicity rates, a lot of exhumation, and slow cooling in the Eurasian margin beginning at 30, really rapid cooling beginning at 5. In Azerbaijan and the Eastern Caucasus, rapid GPS closing rates, high seismicity rates, about 3 kilometers of exhumation, but a difference between Eurasia, which cooled slowly from 30 to 5, and then began cooling fast, and the portion south of the main suture, which potentially would be buried before 5 before turning around and rocketing back up to the surface. So these are kind of the data pieces we have to work with. Just look at the GPS velocities again to remind you of that fact. Slow here in the Western Caucasus, increasing rapidly here to the Eastern Caucasus, deep exhumation here, less exhumation here, but all beginning at roughly the same time. And then to remind you again, something interesting about differences between the Western Caucasus and the Eastern Caucasus. We showed this before, but coming back to maybe putting these pieces together. Here we have a big piece of Precambrian massif called the Jorullo Massif colliding with the southern margin of Eurasia. Over here we have this, what is thought to be transitional crust or thin continental to oceanic crust colliding with the eastern portions of Azerbaijan. And we begin to wonder if these rheologic differences are playing a role in how the Greater Caucasus are responding to this collisional belt. And so what we began to think in the central Greater Caucasus is we have two large continental masses colliding with one another, rigid and old, Paleozoic crystalline basement, Proterozoic crystalline basement, and the response is to focus all their deformation onto a single fault between those two blocks. And even though that fault isn't moving particularly fast, because the motion is all in a single structure, it can lead to a significant amount of exhumation and uplift of the Greater Caucasus Mountain range. We saw this in the GPS as well. We had fairly constant GPS rates, and right at this one structure, they stepped and slowed. And so I think we're focusing all 4 millimeters here on this one structure, and allows us to build a tall mountain range with a lot of exhumation, even though it's colliding fairly slowly in the Georgian Caucasus. In the eastern Greater Caucasus, the deformation is distributed over a much broader zone with many more faults involved in the deformation. By partitioning this 15 millimeters a year across many faults, we can accommodate a lot of horizontal shortening, but we don't need to have as much vertical exhumation. And so we haven't exhumed the rocks as deeply in the eastern portion of the range. And so why is this happening and triggering at 5 million years ago? Well, I'll show you a picture from some of our colleagues in Georgia, and they were able to get for us data that wasn't really available outside of this area. All of these countries have seismic networks, but they put very little of that data online for other people to see. But our Georgian colleagues worked with some colleagues in Russia and some colleagues in Azerbaijan and built this model of modern day earthquakes. And I'll show you a little movie of that. This was assembled by my colleagues at UC Davis. And so we'll fly around the Caucasus a little bit. So the Greater Caucasus here, the Lesser Caucasus here, and all these dots that you see here are earthquakes, color-coded to some extent by depth. And so the colors go from kind of greens and yellows down to reds and blues. And one of the things I want you to focus on is this cloud here, and we'll come back to it in a minute, underneath the eastern Greater Caucasus. These go down to almost 150 kilometers depth beneath the Greater Caucasus, and they only exist under the eastern portion of the range. We're now kind of looking west along the axis, so we're under the Black Sea, the Caspian's out over here. And you can see that these dip to the north, this panel of deep earthquakes. So they're going from shallow at the southern margin of the Greater Caucasus to deeper depths as we go to the north underneath the Greater Caucasus. So here's Elbrus again, some of the volcanism we talked about earlier. Now looking down at Baku, and those deep earthquakes are here underneath this portion of the range. And they extend a little bit offward here under the Caspian Sea. We don't see them at all here under the western portion. Actually, you can see them right there perfectly in a line, right under Kazbek volcano. And so they truncate right here, no deep earthquakes, and then this cloud of much deeper earthquakes here underneath the eastern portion of the Greater Caucasus. And I'll show some cross sections through these in a second and explain what we think they mean. And turn it around one more time.
What time span does this represent?
This is historical seismicity, although their best located data is from about 1980 to the present.
Okay.
In terms of, they did a technique called double differencing to relocate these. And so the absolute positions of these may be slightly off, but the relative positions are really quite good. And so they use earthquakes close to one another to make models of what the seismic speeds are through the crust above them to help better locate the remaining earthquakes. I think this is spinning on a loop here now. All right. So here's some cross sections. So these are, this is the eastern Caucasus here, this BB prime line. So this is south here and north. This is the mostly crustal seismicity. So all this is what you'd expect in a typical continental collision. We're within the continental crust. Now earthquakes should extend down to depths of 150 kilometers beneath the continental crust. Not particularly big ones, magnitudes 4 to 5 mostly. And you can see that they dip off towards the north. Right? So this is south, this is north. As we move to the west along the range, so now we're getting towards Georgia, we can see we still have some of these earthquakes left, extending down to roughly 100 kilometers depth, not quite as deep in eastern Caucasus, and again dipping to the north. And by the time we get to the transects I worked on with thermochronology in the central Caucasus, they're all gone. Everything is in the crust itself. This is a picture here, just looking from, I guess at this point, in this case, it's west on this side, east on this side. So this is Azerbaijan and the Caspian. This is Georgia and the Black Sea. This was the large earthquake Rasha in 1991. And so you can again see this cloud of deep earthquakes under the eastern portion of the Caucasus, no earthquakes whatsoever under the western portion of the Caucasus. And so our tectonic model for this, when we put it together with the timing of exhumation, when we put it together with the geology, we put it together with the seismicity and the GPS, is that under the eastern Caucasus we have the remnants of an oceanic slab that is still attached to the lesser Caucasus and is pulling it into and colliding it with the greater Caucasus. The pull of this slab is the reason why the GPS velocities are so much higher in the east than in the west, because the sinking of this slab is pulling that lesser Caucasus in much faster than where it's not attached to the west. We see that in the earthquake pattern that's going down beneath the range. It helps explain the fast GPS rates. It also explains the relatively shallow exhumation. By pulling an oceanic slab down underneath this portion of the range, the strength of the collision here will be much less than to the west, where we're actually colliding these two big Proterozoic and Paleozoic blocks together with one another. And so what we think what has happened here is that this is telling us the picture of what's going on in the last few million years. If you look at the closure rates between the Greater Caucasus and you run this movie in reverse, you take this oceanic crust back up the subduction zone, and you begin to open up this small oceanic basin that used to lie between the Lesser Caucasus volcanic arc and the Greater Caucasus mountain range. And so about 30 million years ago, when the Arabia-Eurasia collision began, this oceanic plate began to get pushed underneath the Greater Caucasus. The oceanic plate was fairly happy to subduct, and so the Greater Caucasus began to exhume a little bit. But most of the motion between the Lesser Caucasus and the Greater Caucasus was just taken care of by pushing oceanic plate down out of the way underneath the Greater Caucasus. About 5 million years ago, we subducted the last bits of oceanic crust, and we begin to collide this Proterozoic block and this transitional crust with the Greater Caucasus. Now we're colliding two things that don't want to subduct so much. They don't want to go down underneath. We begin to get deformation throughout the range. Because of the rheologic contrast between the west and the east, we're colliding too much more strong blocks in the west, and we build this mountain range very, very quickly and strip the sediment off the top. In the east, we're still colliding a more buoyant crust than we were, but still not full-blown continental crust. And so we're building a mountain range that's seeing less exhumation, even though it's still seeing more rapid collision and closure from the perspective of GPS.
So does your model suggest that there was an oceanic seaway between the Black Sea and the Caspian?
In the past, unquestionably, there has been. Yeah. There's actually, in fact, the seaway in the past extended from the Black Sea, probably to the Caspian Sea, to the Aral Sea. It's been argued 15 million years ago all the way to the Tarim Basin north of the Tibetan Plateau. Probably since about 5 million years ago, the Kura Basin, this area here, holds a beautiful record of Caspian base level change. And I think at least since 5, the Caspian has not filled high enough to breach this divide and connect with the Black Sea. All right, so my conclusions: the Greater Caucasus, we think, are in the early stages of a continent-continent collision, just transitioning from subduction to collision. It's one of the very few places in the world we actually have the potential opportunity to go and explore how this process happens and what the geologic response is. Variations in geodesy, seismicity, and geological structure along strike of the Caucasus can be used to understand this transition and how rheological variations affect continental orogenesis, and the consumption of a small ocean basin within the Arabia-Eurasia collision zone may be something that can help resolve discrepancies between plate motions and observed upper crustal shortening. The consumption of the ocean basin from 30 to 25 million years ago left very little record in the Greater Caucasus until it finally completely closed about 5 million years ago. So, all right, thank you.
Questions for Nathan?
Is there any rotational aspect seen between the difference east to west and these pressures and subductions? Is the whole mass rotating one way or the other?
That's a good question. So, in terms of a kinematic perspective right now, it appears that the Lesser Caucasus basically are swinging like this. The test of that would be looking at paleomagnetic field vectors in rocks and seeing if they're rotating as a function of time. And there's a group in the Netherlands that currently is pursuing that. If the Caucasus had been swinging like this for a long enough period of time, you can predict. If the rocks were originally oriented like this, for example, and then you froze a magnetic field and then pointed north, as those rocks swing, or the paleomagnetic vector changes. And so you could sample it and ask, is it still pointing north functionally? And so people are working on that to look at rotations in the Caucasus.
Have you applied that thermochronology to local mountains?
To local mountains?
Yeah, like the Tetons?
I personally have not, but it has been done. Yeah, it's a guy at Virginia Tech named Jim Spatilla who had a student apply the very lowest temperature technique I talked about to the Tetons. And there's a slightly higher temperature one, sensitive to about 120 degrees C, that was applied by a guy named Doug Burbank and one of his students back in the late 90s. And if I remember correctly, their conclusion was the Tetons began to exhume at roughly 15 million years ago and sped up a bit around 9.
Would you compare the Caucasus to the Himalayas? And I'm kind of curious from a timing, the amount of foreshortening between the two. Obviously, the Himalayas is a whole lot more collision foreshortening, but then the involvement of the oceanic plates and the timing of all that. Can you kind of compare and contrast the two collisions?
Yeah, and so obviously Himalaya are the collision of India with Eurasia. In terms of contrast, that one started quite a bit earlier. Most people seem to be focusing on roughly 45 million years ago as when you could have walked from Asia to India. You closed Neotethys, which was the same ocean basin, but as far as we know, that portion of Neotethys did not have a lot of intraoceanic island arcs or intraoceanic basins. It was the model of the Himalaya would have been, up until collision, something very Andean. And we see that in the geology of the Himalaya. There's a huge batholith called the Gandhisi batholith that was probably, like, if you stripped the volcanic edifices off of the Andes, that would be beneath them. And so for the Himalaya, you had Asia, and you just had oceanic subduction beneath it. And that went on for many, many tens of millions of years. And in the final stages of that oceanic closure, India came in and collided with the Himalaya. That arc shut off. One of the other contrasting points is India is obviously a subcontinent, but a very, very large landmass. And the margin of India that came in to hit Asia was much like the margin of the east coast of the United States today. It was a huge passive margin with a giant sedimentary pile, right? And then you had a volcanic arc with a huge 4 deep in front of it, right? A trench. And so you have this massive amount of sediments on both continents that then also get involved with the deformation. And that's what you see all throughout much of the Himalaya, are those sediments. Some buried and metamorphosed and brought back up. Everest, of course, is a limestone from this ocean basin that's now been raised to the top. In terms of the Caucasus, about 30 million years ago, Arabia began colliding with Asia, but instead of having a clean oceanic system, you had a much more complex system with island arcs in it, old oceanic fragments in it, continental fragments stuck into it. And so all these pieces kind of get constantly accumulated and banged together as this whole thing collided. So the perspective I would have for this is it's kind of like, the collision was happening in which a bunch of things hit Japan, and then Japan begins to close the basin behind it at 30, and then it finally hits the mainland China at 5. The island arc, the Lesser Caucasus arc, was in the middle of an ocean, has very little sedimentary margin. And so in that perspective, it's very different from India, no big passive sedimentary section. Although there was a good continental margin on the one side, the Greater Caucasus side. So those are some things that are different about them for sure.
Is that the primary oil distribution system from Russia to Europe? And isn't that kind of a difficult place to put it in terms of the seismic activity?
The big pipeline there actually goes to Turkey, to Istanbul. It starts in the Caspian and comes through Azerbaijan and Georgia and then goes into Turkey. I believe continues to Istanbul is where the big one that they worry about seismically at least.
So can you go back a couple slides to where you showed the plate slabs stuff? Yeah. So near the Black Sea, was the slab there previously and now it's well under, or is that the edge of the slab?
That's a really good question. So most people believe that the Black Sea itself is still floored by oceanic crust. And I could go, it might be easier to do this. This is a strangely complicated collision zone. So Arabia is colliding northwards with Eurasia, right? If you see here, from this point going in this direction, that deformation northward is, instead of being accommodated by two blocks colliding, is accommodated by two strike slip faults, the North Anatolian Fault and the East Anatolian Fault. And so this fault here, this side moves this direction, and this fault here, this side moves that direction. And you can imagine it like a big wedge, just getting a watermelon seed getting squeezed out, right? And so the shortening is happening this direction, but the way you're accommodating it is taking this wedge and just squeezing it out of the way. Right? And so that's probably one of the reasons why the Black Sea is not currently getting shoved underneath the Greater Caucasus. As all this, Arabia is moving this way, here it's just getting accommodated by this going that way. Okay? But here, you don't have that set of faults. And so this is moving northwards towards the Greater Caucasus, and it's all getting accommodated right here along this suture zone between the Greater Caucasus and the Lesser Caucasus. And so that's why I think the Black Sea is a bit of a different story, starting probably, roughly west of this line. But did the oceanic plate exist underneath this portion of the Greater Caucasus? I'm inclined to think that the answer is yes. And the reason I'm inclined to think it is because of the volcanism here. One of the side effects one would expect from tearing a plate off, oceanic plates like this are actually refrigerants. They're cold, they're dense, they're covered with cold sediment, and as you shove them underneath the continent, you actually chill the continent. Right? If you tear it off, you allow the hot asthenospheric mantle, from underneath them to well up underneath the continent. And so I suspect that volcanism is only expressed in this portion of the range because the slab has been torn off, and that allows hot asthenosphere to be exposed right to the bottom of the continental plate, rising the temperatures quickly, and then generating melts that lead to these eruptive units over here. That'd be my suspicion. There's a big project finally starting. There's tools to look at this kind of thing called tomography. Yes, yeah, they do it all over. The challenge was getting the Russians to agree, because one-sided tomography isn't very helpful, right? And so Azerbaijan and Georgia and Armenia were all on board with putting out seismic arrays to do tomography. But imaging underneath the Greater Caucasus was only going to work well if you could also put instruments in Russia. And so I think a group has finally come to an agreement to get that done. And you'll be able to actually finally look at seismic rays passing both ways through the mantle underneath the Greater Caucasus. So one thing, we see this with earthquakes, right? But if there's a slab that's detached and is now sinking through the mantle, right, that's no longer seismic, the only way we'll actually ever find it is with seismic rays that pass through it and observe its change in density and velocity structure. And for that, we need tomographic imaging as part of the world. But I'm hoping that gets started with a group out of University of Missouri next summer.
Could you go back to that last slide with the fault line? What has happened to the BKF fault?
Which, could you say that a little louder, please?
He asked what is going on with this fault, the BKF fault. So BKF, it stands for Borjomi, which is a town in Georgia, and Kazbeki, which is the Kazbek volcano, which it points towards fault. I put it on here as a marker of location because it's been prominent in the studies of this part of the world for a long time. A number of people have gone out and studied it. They find absolutely no evidence that this fault actually exists on the surface of the Earth. Here's my personal feeling. There's some deeper geophysical evidence for it. And that's it's not well studied. This here, West Caspian Fault, the sedimentary thicknesses triple from here to here. So this has accumulated, I'm going to say, 10 to 12 kilometers of sedimentary strata in the last 6 million years. But the question was, was it because this was moving and actively accommodating, or was it already there passively? And so one interpretation of these faults is that they're actually old transform faults associated with the formation of this back arc basin. So this would have been a basin, the South Caspian Basin, as you were forming this back arc between the Lesser Caucasus and the Greater Caucasus. There was a transform fault, and there would have been another basin, and a transform fault in the Black Sea. So that's the most likely interpretation for these. This doesn't have any seismic activity associated with it, but it has other interesting features. All of the volcanoes, for example, lie west of the projection of this fault. Now you look at helium signatures, helium exhaling from the mantle in terms of hot springs. It's incredibly helium-rich here and here, but not here and here. And so there's reasons people think that there really is a structure of depth, but I don't think it's an active fault in the sense of controlling deformation in the Greater Caucasus today.
Have you seen any data across the Asperson Arch?
Across the
Asperson Arch.
Oh, yes. And so, yeah, actually the deep seismicity extends across the Apcheron sill as well. And so, yeah, this is the Apcheron Peninsula here on which Baku lies. And there's a bathymetric feature that separates the South Caspian from the North Caspian and extends all the way across here into Turkmenistan. There's another big fault over here and another mountain range here called the Kopet Dagh. And so circulation in the Caspian Basin is restricted by this sill, they call it. The water level is much lower because this sill is, I think, a kilometer higher than the rest of the surrounding Caspian floor. Yeah, so there's clearly a structural feature that extends across the entire Caspian here, and it's thought that the oceanic crust of South Caspian is actually getting shoved northwards underneath the North Caspian. There's seismic evidence for that. I haven't seen any offshore seismic data. Seismic data in this part of the world is incredibly difficult to get your hands on.
It looks exactly like your cross-section on the eastern Greater Caucasus.
Right through here?
Yeah.
Yeah, okay.
I saw that and I would have told you that's exactly what projects on the cast.
Did you mention a caldera volcano early in the talk?
Yes, I did.
And where does that fit related to the picture where you have the plate subduction, the oceanic plate? I think it's the next slide or the previous one. Where you showed your conclusion. Yeah,
this one here?
Yeah, where's the caldera volcano?
It's actually right here. It's called Chegem.
And does that fit into the story somehow?
Yeah, I mean, it was studied, there's a bit of détente in the late 1990s, and the U.S., some of the really top volcanologists from the U.S. Geological Survey were allowed to come over here and work. And so the guy who worked on this is a guy named Peter Lippmann. He's done work on volcanism all throughout the Western United States. I think Christensen and Lippmann, in fact, is the Bible of Yellowstone volcanism. And so Lippmann's description of the types of volcanic rocks found here, their geochemistry, their eruptive characteristics, is very much like a continental margin arc system, and very much like things that have happened in the Western United States. They're erupting through continental crust, probably the result of subduction that is waning. San Juan volcanics, for example, in Colorado, was something very similar to this style of eruption, or even Long Valley And in terms of size, it's a great analogy for Long Valley. You can drive up in here, and the entire valleys are just nothing but volcanic ash, like hundreds and hundreds and hundreds of meters.
Yes. Anything else? Any last question? If not, sort of the usual. 2 weeks' time, we've got Larry Lauber, University of Texas at Austin, will be here to talk about plate tectonics in general, and then he'll focus in specifically on the Caribbean, basically, and Cuba. So that should be, it'll be very interesting. He'll give a little bit of background about where plate tectonics sort of came from. I mean, some of us go longer. Some of us actually remember when that was, there was actually still controversy about that. But, and let's see, and then he will also give a lunchtime talk the next day after that. Then, of course, the eclipse happens. So,
Before that, make sure you talk to Brent as far as the barbecue.
Yep, talk to Brent about barbecue. In just a moment, we will ask you to move chairs like along the side there. And Nathan, this actually has been sitting in my closet for a year. It's a little gift for you.
Oh,
so the date on it is 2016. Because some of you will remember that Nathan actually was scheduled to give this talk basically a year ago. And then crows got into the transformer in southeastern Idaho, and the power went down regionally. Just about the time you arrived, you pulled up in the parking lot out here. So if you would join me in thanking